Hi, we are now going to take a look at a method of analyzing the boundary layers that was first proposed by the von Karman in 1921, and this technique is one that results in approximations for the characteristics on the descriptions of the boundary layer, mainly the growth rate as well as the skin friction coefficients. Okay, the reason why we're going to spend time looking at it because of it used the tool that we have developed, we have studied in the previous course, which is in the introductory course, fluid mechanics 1, and this also using the control volume analysis, which is if you remember, you have learned in the fluid mechanics 1 what we call it the Reynolds transport theorem. So we're going to use that in this chapter, or in this momentum integral theory. So what von Karman did is apply the control volumes, as shown here, to analyze the study the flat plate boundary layer, and it was able to come up with some really quite remarkable result during considering the approach that he took, in the fact that it was really very basic analysis. Alright, after that, consequently, we will doing it looking at that and refer as a von Karman momentum integral theory. Okay, von Karman, if you know, is analyzing the flow over the flat using the boundary layer control volume analysis and using the momentum equations. So there are more advanced methods that are developed by Prandtl, but we first are looking at this von Karman first. All right, we look into the these figures, and then if you've seen here, I put this as number 1 here, which is a, and then this is a 2, and then I put this as a 3, this surface, and then the last surface I put number 4. All right, we're going to study this systematically of the boundary layer von Karman, and then we try to solve it, and we try to solve this case. All right, we have defined the control volume as shown here. So we know that this is the what we call it the flux. So when the flow come here, this is, we call it the mass flux inlet, or mass flux. Mass flux ins. And here, at this surface, this is mass flux out. All right. From this mass flux in and mass flux out, and then we can apply the control volume. All right. Let's look into the first. We apply the continuity equations. So look into these continuity equations. This continuity equation we derive from the Reynolds transport theorem, which is you have studied in the fluid mechanics 1. So we know that the first term of the right hand side is also equal to 0. This is because there is no change in the control volumes for the density. So this is equal to 0. And then in this side is actually, if you look into we recall the Reynolds transport theorem. You recall the Reynolds transport theorem. In the Reynolds transport theorem, they said that d dt for any system, this is equal to d over dt, sorry, this is a del over dt, del over del t, so integrate the control volume, which is the beta rho dv. This is a control volumes, and then the plus the control surface beta rho v dot n. All right. So in this case, we know that the B is actually the, in this case, the B is actually the mass. So when the mass we differentiates to the change of rate of mass to the time, this is equal to 0. That's why we got the 0 here. So we have a 0 here. And then the rest, the beta, actually the B over mass. Right? This is mass. So this is a quantity. So anything, the quantity, for this case, the quantity is mass. So mass divided by mass is equal to 1. That's why we didn't put anything in front of this. All right. So now, if we solve this one using this, we know that from the Reynolds transport theorems, then we have the rho minus rho 1. Actually, this is if you solve this from these equations, from the Reynolds transport theorem, what you have, if you solve in this one from using the Reynolds transport theorem, this is what you have. We got it's actually the rho 1 multiplied by v1, and then you got the minus 1. Why is minus 1? Because of we know that this is the n, this is the n opposite the directions of the flow, which is the flow come from here. So that's why this is a minus 1. And then we derive, we got it a, right? And then we plus the rho v2, and then multiply by 1. Why 1? Because at the outside, the n always the perpendicular to the surface where the flow out. So at this surface, the velocity also in the same directions of the n. So now n is 1, and then we got the, we multiply with a. All right, a1 and a2. All right, this is how we got these equations. All right, and then from here, if you look into these figures, okay, what we can see here in this figure, the rho is a rho here, so we have rho, and then u is the u naught here. So we have the uniform flow, which is they come as a uniform flow. That's why we have a uniform flow here. And then the area, actually the y equal to h, and the b actually into the screen. So that's why we have a minus rho u naught hb, because hb is a1, this is a v, this is a v1, this is the a. Right, from there, then the second part is the, okay, we have the rho, which is a rho b. Why I didn't put 1 and 2? Because of the density is incompressible. So we assume that rho constant everywhere in this flat plate. All right, so now from here, the b we integrate. So the u is the velocity here, the v2 is not a constant, but is a change due to the, with respect to the y. That's why this is a v. And then the area as well change with the respect of y. So that's why we have this equation. So then if we simplify this one, what we can see now, the answer that we have, actually the rho u naught hb equal to rho b integrate from 0 to theta u dy. So if I simplify this equation, so I got the value for hash equal to 1 minus u naught integration from 0 to delta u dy. All right, now we use another control volumes equation, which is a momentum equation, by putting the momentum equation. So now dB in the dm, this is equal to m dB dt. So what we can write here, this is equal to ma, and then we know this is a force. All right, so now the force is equal to, against in this part, if we differentiate this to the control volume, it doesn't change to the with respect to the time, and then this one also equal to 0, similar as the previous one, and then this one we have this v dot rho v dot nta. All right, so we solve in the x direction. First, we look into the x directions. So if we have a normal drag here, since this is a free flow, we didn't have any drag in the front of this surface of the control volume. However, at the phase number 4, if you still remember, at the surface 4, at this we have the force, the drag on the uh, plate, because of this drag would counter the flow through to this plate. So the force that we have here, summation of force, is now become to minus dy minus, because it's opposite direction. The flow come from here, and then the force that against the flow opposite direction. That's why this is minus d, and then u naught, the velocity. So if you have here, we got the u naught. If you simplify this one, this equation can change into this one, this form. So you must remember this, how to determine this. So before you come up with this, what we have actually the minus rho u naught. All right, so this is minus rho u naught multiplied by u naught. Okay, and then we have multiplied by, for the end is a minus 1. Okay, sorry, I make a mistake here. So this is not minus. So we plus 1. And is a minus 1. So we plus a minus 1 here. And then we plus with the area. Multiply by the area. And then again, here we plus b. So we have rho. Again, we have the u, which is u with respect also to the change of u is due to the change of y. So then that's why we have this equation. So we integrate from 0 to delta u, and then we have u b dy. So you can write like this in the original form. Actually, we have rho u squared a minus plus rho u squared a. So we can transform to this form. So we can see here. All right. So uh, from here, so if we do some arrangement or simplification for this equation, then it shows that the d equal to rho u naught squared bh minus rho p integration from 0 to delta u squared dy. So when we introduce the hash from the continuity equation, so we know already the value of hash. So now we try to solve this hash. So we put the hash here. So from the if from here, so from here you got these equations. So these equations, we bring these equations, okay, to this one, to here. Okay. Right, so these equations, now you substitute into these equations, okay, you can see here, then and you substitute these equations to here to replace the value of h, then what happened, the original equations now can change into this. So now the d equal to rho u naught squared b 1 over u naught 0 to delta u dy minus rho b 0 to delta uh, u squared dy. So we try to solve this one first. So we when we look at this, we can see the similar thing that we can factorize this or simplify this equation. Now we have the d equal to rho b integration from 0 to delta u naught u multiplied by u naught minus u dy. So these equations can be written as the dx equal to rho b u naught squared theta, which is I put this as equation number one, and I don't know this theta, but I put the theta as the momentum thickness. Right? What is momentum thickness? Momentum thickness. So this is a momentum thickness of the boundary layers. All right. The drag can also be written. The drag dx also can be written in terms of wall shear stress. So the dx equal to the b. Actually, you know the drags for the shear stress. Actually, the areas to the top. This is the shear stress that we have from uh, the drag that we can get from the shear. Right, so now if you simplify this one and then using this, because we know that it's a respect to the distance of the flat plate, so we don't know where the x, so we say that this is a change to the x. So d dx is equal to the b tau w. So I put this as equation number 2. And now we equating the momentum equation drag, which is equation number 1, with a wall shear stress drag, wall shear drag, which is equation number 2. So if we equate this d dx, and then we also have d dx here in this equations, or this equation. So if these equations you take a d dx, so and then we equate these two, so we have d dx equal to rho b u naught d theta dx equal to b tau wall. So now in this case we can written this as tau wall equal to rho u naught d theta dx. So these equations actually can be used either for laminar or turbulent flow. This is valid for laminar or turbulent flow. Alright, the velocity profile. Now we go to the velocity profile, the assumptions of velocity profile. We cannot get the exact using the von Karman. Actually, the assumption velocity profile only can get, and then the approximations of the velocity profile. So for the laminar flow, von Karman assumes that it's a quadratic velocity profile. So what he assumed here is a quadratic velocity profile, and this quadratic velocity profile given by these equations. So u equal to the a plus b plus by plus cy squared. All right, we can use the boundary conditions here. We can see the boundary conditions here. We can apply the boundary condition here. For example, okay, I take this boundary. I draw here the boundary conditions. All right, for the velocity profile. Let's say we have the velocity profile here in the flat plate. So this is the flat plate. All right, we have the boundary layer here. So this is our boundary layer in the flat plate, and then we have the velocity profile at the viscous areas. So this is a velocity profile. All right, now this is a at y, and then this is right? Here is y. Okay, this is x, which is here at this point is x equal to, at this point x equal to 0, and then at this point also y equal to 0. Okay, now we can take like this. So the boundary condition, we said that at u at y equal to 0. At y equal to 0 means that here, at this point, there is a no slip condition. So no slip condition, this will give you u equal to 0. So in this case, that's why at y equal to 0, u at y equal to 0 also equal to 0. So we substitute this into this equation. So we have the 0 plus a plus b multiplied by 0 plus c multiplied by 0. Then with that, we get the a equal to 0. Next, we go to the, all right. So let's say now the velocity, this is the delta. Okay, this is the boundary layer thickness. I put this as a delta, the boundary layer thickness. At this position of the boundary layer thickness, at this point, if we differentiate this one, so we differentiate the velocity with respect to the y at this point, because there is no change in the velocity above the boundary layer. So there is a similar velocity which is above this all is a u naught. So then from here we got the at y equal to delta, y equal to delta. So the value for the velocity also equal to 0. Okay, now at d dy, y equal to delta equal to 0. So the velocity at this du dy equal to 0 at y equal to delta. So we substitute here du dy. So we differentiate this equation du dy. So what we got here is actually the y plus 2cy, right? 2cy. So we know that if at y equal to delta, so we substitute y equal to delta, du dy equal to 0. So that's why it's 0 plus the, all right, sorry, this is my mistake. This is not y, but this is a b. Okay, this is b. So du dy, we got b because we differentiate this one. So b equal 0 equal to, we substitute the b, we still get b here, and then we substitute the y, we replace by delta. So now if we do some simplification, we got the b equal to minus 2c delta. All right. Furthermore, we do the another boundary conditions, or we apply another boundary condition to this velocity profile, and then we know that at y equal to delta, u equal to u naught. Okay, again, if you this the boundary layers like this, the velocity profile, our velocity profile like this. So at y equal to delta, which is equal to the boundary layer thickness, we know that above this the velocity u was equal to u naught. Alright, so now we substitute here in this equation u naught equal to the b delta plus c delta y squared. So we already know that the b equal to minus 2c delta, so we substitute the b equal to 2 minus c minus 2c delta. So here inside this, and then we have the u naught equal to minus c delta squared. Then from here, we got c equal to the u naught plus minus u naught divided by delta squared. All right. So we already have the value for a. We also have a value for c. But now we can solve to get the value for B. So from these equations, from this C and A that we know, and then we can substitute to the original equations. So what is the original equations that we have, or we can put in any equations that we have here. So I prefer to put the original equation. So uh, we have this one. So we know that the B equal to minus 2C delta. So you substitute these equations back into this one. So put it here. And then we have the B equal to 2 U naught delta. Alright. Then now we already have the value for A, B, and C. So what we're going to do now, we substitute all these equations back into the original equations. So back into, we put the A, B, C, D into the A, U equal to A plus BY plus CY squared. So we substitute back into this. So then after do some simplification, the equation that we got is actually U equal to 2 u naught y over delta minus u naught y over delta squared. So u over u naught is equal to 2 y over delta minus y over delta squared. Alright, now what we're going to do in the next is we want to calculate the delta or the bond relatedness as well as the coefficients of friction CF in the following topic.